Hi, this is Jeffrey Schmidt of Jeffrey Schmidt Music, and this is course number 7 in Audio Recording 101, where we help the musicians that are non-technical understand what's going on from a technical point of view enough so that you can work with the technical side of audio recording. So in our last episode, number 6, we talked about what sampling rate means. And in number 7, we're talking about what does bit depth mean. I also could have entitled this, what does 16-bit audio mean? Or I could have entitled it, what does 24-bit audio mean? And by the end of this, you should understand what that means. So here we have our audio, same signal that we saw during number 6. Here it's been chopped up every millisecond. We've taken a sample of our electric signal that we had before in red, which I've taken off of the diagram. And now we know that computers and digital devices only speak in ones and zeros. Or another way to say it is they speak in binary. Right? We have a system of digits that we use that's called base 10, where we use the digits from 0 to 9, that's 10 digits, to represent our numbers. And here, computers use only 2 digits from 0 to 1. So it's called base 2, a base 2 counting system or number system, or you could call it binary. And so, when we want to send the values of the signal to a computer, we need to code them in terms of binary. So here we're going to suppose that we have a signal, just like before, that we know is going to be between minus 4 millivolts and 3 millivolts at most. Okay? And you'll notice that if you count the numbers from 3 to minus 4, we have 8 numbers. Well, I planned this example out that way because 8 is a power of 2. So to understand why you want to have a power of 2, you have to see that, just like I said, every bit, which is either 0 or 1, that's what bit means in computer or digital terminology, is represented by 0 or 1. So for the first digit of our number, we have 2 possibilities. For the second digit of our number, we have 2 possibilities, 0 or 1. And for the third digit of our number, we have 2 possibilities. So, if you want to calculate the number of possibilities that we can encode with 3 bits, that's 2 times 2 times 2, which is 2 cubed, or 2 to the 3rd power, which if you calculate equals 8. Okay? So now, I've arbitrarily said, well, I'm going to start counting in binary, and I'm going to encode my millivolt digits in binary now. So I'm going to say that minus 4 is equal to 0, 0, 0, minus 3 is equal to 0, 0, 1, minus 2 is 0, 1, 0. Here I'm just counting upwards in binary, all the way up to 1, 1, 1. The highest 3-bit integer that I can encode in binary. Just like 999 is the highest base 10 number, the numbers that we're used to working with, that we can encode with 3 digits in our base 10 number system. So, as we go along, all we're going to do, we already know where we're going to sample our signal, every millisecond. And here, my signal at 0 milliseconds is equal to 0 millivolts. So I'm going to send along 100, because that's how I chose to define it. And at 1 millisecond, as we saw in the last example, my signal is equal to 2 millivolts, which I've chosen to encode as 110. So that's what I'm going to send over my digital cable, whatever it might be. It might be in SPDIF format, it might be in ADAT format, or it might be in USB format if I'm sending it to a computer. And just to make sure you understand, I'll go on to, at 2 milliseconds, I see that my signal has a value of 3 millivolts, and I've chosen to encode 3 millivolts as a 111 in my 3-bit sampling scheme, and so I'm going to send 111, and that's the same value that I have at 3 milliseconds, but at 4 milliseconds I have a signal that is equal to -1 millivolts, which I've chosen to encode as 011, etc. So there aren't any 3-bit A to D converters, but if there were, this is one example of how it could work. And as I said, a 3-bit A to D converter would give you 8 different amplitudes or signal levels that you could encode. So now let's talk about more real-life examples, which would be basically too difficult to draw. 16-bit conversion. Well, if we want to calculate how many different amplitude levels we get out of 16-bit conversion, we calculate 2 to the 16th power, just like we calculated 2 to the 3rd power here to get 8. And we get 65,536. So you know, if you're working with 16-bit audio, this is the maximum number of amplitudes or different steps in terms of the signal level that can be encoded. If we look at 24-bit conversion, which is another common standard, we calculate 2 to the power of 24, which is 16,777,216 different steps of amplitude that we can use to encode our signal. So if you weren't aware of it, right, because some systems still use 16-bit audio, and some systems use 24-bit audio, and some engines these days use even 32-bit audio. How much more accurate is 24-bit audio than 16-bit audio? Because here, just for the sake of simplicity, I didn't show it. But in future videos, I'm going to develop this more. Here I had a signal, just for the sake of simplicity, that was exactly an even number of millivolts. But what happens with this system if my signal is at 2.5 millivolts? Then I'm going to have to choose to either round it down to 2 millivolts or round it up to 3 millivolts with my 3-bit sampling scheme. Meaning that there's going to be an error in the signal. So what we're really doing when we're increasing the number of bits is we're decreasing the amount of error in the amplitude of the sample that's taken. So how much more accurate is 24-bit conversion compared to 16-bit conversion, or 24-bit audio versus 16-bit audio? Well, to see that, we just have to take the ratio of 24-bit audio to 16-bit audio. So we divide 2 to the power of 24 by 2 to the power of 16, which is 2 to the 8th power, which equals 256. So if you weren't aware of it, using 24-bit audio is 256 times more accurate than 16-bit audio, meaning that you're going to have 256 times as much error in your signals when you use 16-bit audio instead of 24-bit audio. And we could do the same calculation if we wanted to compare 32-bit audio to 24-bit audio. It actually comes out to the same thing, because 2 to the 32nd power over 2 to the 24th power is also equal to 2 to the 8th power, which is 256. So we could also say that 32-bit audio is also 256 times more accurate than 24-bit audio. So as we go along in these courses, this idea of error, which I just introduced for the first time in this episode, is going to become more and more important to understanding why you might want to use very high bit depth, why you would like to use, at least in terms of audio quality, you want to use 32-bit audio if you can. If 32-bit audio is not available, most samplers these days, when you record, use 24-bit audio. Well, you certainly want to use that rather than 16-bit audio or something less than 24-bit audio. And if you do, you can do the experiment if you have converters that allow you to change the bit depth. And well, I can hear the difference. The difference between 24-bit audio and 16-bit audio is pretty easy to hear. 16-bit audio was used originally when they first had digital systems in audio in the 1990s, and at that point they were only used for mastering. And using 16-bit audio for mastering as the final step is acceptable, and that's why the standard on CDs is 16-bit audio. But if you actually record your vocals, your guitar, your bass, your drums, all at 16-bit, and then you try to mix it at 16-bit, and then you try to master it at 16-bit, what you're going to hear isn't something you're going to like. Which is why in professional audio they've never done it that way. They waited for 24-bit systems to come out before they actually started recording in a digital format. Right? Originally, in the 90s, they were still using tape to record, and only in the final step of mastering, for your stereo master, just 2 channels left and right, did they use 16-bit conversion, which is still the standard today for CDs. But again, I wouldn't recommend recording at 16-bit audio. You can, but you probably won't like how it sounds, at least compared to 24-bit audio. Alright, that's all for this episode.